Hello everyone, welcome to this session. I am Dr. Asha Thalange and today we are going to learn single phase half wave controlled rectifier using resistive load. At the end of this session, you will be able to explain the operation of single phase half wave controlled rectifier using resistive load, derive the expression for average load voltage and current, state the advantages of controlled rectifiers over uncontrolled rectifiers. These are the contents we will be covering in this session. Before actually starting, let us recall the rectifiers. We all have studied rectifier circuits. So, rectifier is a circuit which is used to convert an AC to DC voltage. Now, pause the video and let us recall the working of half wave rectifier circuit using a single diode. Now think whether the average DC output of this rectifier can be controlled for the fixed input. The answer is no. The average load voltage for a half wave rectifier is fixed and is given by EM by pi, where EM is maximum input voltage, and such type of rectifiers are therefore known as uncontrolled rectifiers. Let us now discuss what are controlled rectifiers. Well, controlled rectifiers are AC to DC power converters which are used to convert a fixed voltage and fixed frequency AC signal into a variable output DC voltage. These circuits use phase controlled thyristors to obtain variable output DC voltage. Also, single phase controlled rectifiers are further classified into two types: half wave controlled rectifier and full wave controlled rectifiers. Let us now see the working of single phase half wave controlled rectifiers using resistive load. Figure shows the circuit diagram for a single phase half wave controlled rectifier with a purely resistive load. As shown in the figure, in this type of rectifier, single thyristor device is used instead of a diode to provide a controlled output in only one half cycle of the input AC supply and is connected in series with the load resistance. Let us now understand the working of this half wave controlled rectifier using the waveforms. Figure shows the waveform for supply voltage Vs, firing pulses or also known as gate current pulses Ig, load voltage EDC across the load resistance R, load current IDC through the load resistance R, and lastly voltage Vt across the SCR. Let us see how it works. Now, during the positive half cycle of the input supply voltage, SCR is in the forward biased condition, but it will not conduct as it is not triggered using the gate pulse. Till then, SCR acts as an open switch and hence all the supply voltage appears across the SCR. Also, due to this, the load voltage and current across the resistance will be 0. The moment gate pulse is applied at a delay angle or firing angle alpha, SCR triggers and acts as a close switch. Now, this makes the voltage across the SCR to drop to a forward conducting voltage which is very small, and thus now all the supply voltage appear across the load resistance. As the load is resistive, current is proportional to the voltage and thus follows the load voltage. This continues till the end of the positive half cycle of the supply voltage. And thus we can say SCR conducts during omega t equal to alpha to pi. The moment negative half cycle appears, SCR becomes reverse biased and due to natural commutation, SCR now turns off. This makes all the supply voltage to appear across the SCR and load voltage and load current becomes 0 again and this state continues till the next gate pulse is applied to turn on the SCR at an angle 2 pi plus alpha, which then repeats the same process. Thus, we can say load voltage EDC is given by Vm sin omega t and load current IDC is Vm sin omega t upon R, where omega t varies between alpha to pi. Let us now see the effect of different firing angle alpha on the load voltage. As shown, when the firing angle is increased from 0 degrees to 135 degrees, conduction period of SCR is reduced, which makes the average load voltage to reduce. Thus, we can say that average load voltage is inversely proportional to the firing angle alpha. More is the firing angle, less is the average load voltage and vice versa. Let us now derive the expression for average load, output voltage, current and power. We know that average value of any function f of x can be calculated using the expression average value is equal to 1 upon t integration from 0 to t into f of x dx. Thus, we know that average value of any function f of x can be calculated using the expression average value equal to 1 upon t integration from 0 to t f of x dx. Thus, average value of output voltage for single phase half wave controlled rectifier can be given by EDC is equal to 1 upon 2 pi integration from 0 to 2 pi Vm sin omega t dt. As we know, the output voltage is present only during omega t equal to alpha to pi. Thus, substituting the value of output, solving the integration and putting the limits, finally we get EDC is equal to Vm by 2 pi into 1 plus cos alpha. Thus, it can be seen that EDC depends on firing angle alpha. Also, when the firing angle alpha is 0 degrees, the average voltage is maximum and is given by Vm by pi. Similarly, average load current is equal to EDC upon R and is given by Vm upon 2 pi R into 1 plus cos alpha. Also, power transferred to the load is given by square of the average output load voltage divided by R. Thus, we can say that power and voltage can be controlled by firing angle. Thus, in this session, we have seen the working of half-wave controlled rectifier using resistive load and derived the expression for average load voltage and current. These are the references used. Thank you.